So I think we are live. So let me share my screen. So can you confirm that you can see the slides? Anyone?
Yes.
Yes.
Okay, thank you. So in the last class, we were looking at autonomous DNA models. We started actually autonomous DNA models. So especially abstract tile assembly model. Briefly, we described a few things there. So I am going to do a couple of more examples today, and especially we are going to focus on error correction mechanisms, how errors are corrected, because I think you might have seen in the simulation that some sort of red spots were there when we do the simulations, and those are the points of mismatch error, right? So let me show you uh, what are the kind of errors and how to correct them. And I am going to discuss two of them basically, which are important. So remember, algorithmic self-assembly is a combination of Wang tiling, DNA nanotechnology, and biomolecular computation by Edelman, which was started by Eric Winfrey, who gave the foundation. We are going to look at the exact results of Winfrey in our future lectures. So these are the Wang tiles, and you remember why we look at Wang tiles, because we are looking at molecular. So basically, we are looking at double crossover molecules or triple crossover molecules of net semen. So Winfield proposed molecular Wang tiles, a combination of those ideas. And see, so remember, this is a double crossover molecule, as you can see that here. So let me show you. So these strands here, this one, this one, this one, these are the free strands of double crossover molecule, and there are 4 here also, right? So these two, so one of such strand corresponds to a tile, something like this. Another one will correspond to another tile like this, right? In abstract sense. And these colors corresponds to these free sticky ends. So the colors have some glue attached to it, and there are some glue strength. Okay, so they can attach to itself, and then of course there are forward rate reaction, backward rate reaction. So so they can combine. Okay, so I'm just recalling what we have done last time. So in the abstraction sense, this is the DNA tile. We have glues attached to it, glue strength, and some color. Okay, so for example, capital A has strength 2, other glues C, D, B have strength 1. Okay, so in the abstract tile assembly model, a tiling model is an arrangement of different tiles that fit together perfectly in a plane. A tile system is a quadruple, capital T, capital S, G, and T. Capital S is the initial configuration. Capital T is where supply of tiles are there. Small g is the glue strength, and T is the temperature of the system. So for example, if you look at this arrangement here, this is known as initial configuration, as you can see here. And a free tile like this can attach to the system. First, the glue color should match. As you can see that the symbols are matching, A1, A1, A2, A2. And then the binding strength. Here the strength is 2, here the strength is 2, here strength is 1, here the strength is 1. If the combined strength, the total strength of the matching glues is greater than or equal to the system temperature. Here the system temperature is assumed to be 2. So then this tile will attach here. Okay. So this is the arrangement. So this is how the tiles will attach. Here is an example. Temperature is 2, and you can see that so initial seat configuration is this, and there are supply of tiles. There are enough number of tiles of this kind. Then what will happen? As you see, this red will attach, because why? Because here it is V symbol and the strength is 2. Here it is V symbol and the strength is 2. So this and this 2 will combine, right? First the color should match, which is V, which is matching, symbol is matching, and then the strength is 4, which is greater than or equal to system temperature. So they will attach to it. So this is how this will attach. Now there are two things. Now if I want to attach a tile here, I need a tile on the left corner, there should be X, on the bottom there should be Y. So which tile can match here? You can clearly see this green tile will attach possibly, right? And of course the strength should match. So here strength is 1 1 1 1, so total 4. So obviously this will attach here. So you can see that this will attach here, right? So this is how the whole system will go. Any question at this point before we start a bit further? Any question about this attachment of tiles? You can say yes, no, anything, Any question?
No, sir.
Okay, good. Now, so I think I have already told you I am going to talk about these DNA complexes in my future lectures, how these things will correspond to this main result. This I have already talked about it. So we now are going to focus again on the binary counter system, the self-assembly of binary counter. We want an array of this kind, so you can see that we have 0, 1, 2, 3, 4, 5, 6, 7, 8, right? Growing like this. So we want to create this kind of thing, and for this we require 4 computational tiles and 3, 1 seed tile and 2 frame tiles. So I mean, this is the types of tiles. So there are enough number of supply of these tiles. Okay. So 7 types of tiles you require. And I think as I mentioned to you in this we have this function here. So these tiles can be described easily with respect to these functions. So output 1 is XOR of input 1 and input 2, and output 2 is AND of input 1 and input 2. So where here is the input 1 from this direction, input 2 from this direction, output 1 from this direction, output 2 from this direction, right? So you can see that these tiles satisfy the requirements, and of course the value of the tile which is 0 here, for example, is copied from the top. The value of the tile is copied from the top here. This is the arrangement where we can grow the tiles. I think I have shown you this picture earlier, that here is a pattern that is created by this. Why we will create by this? Because first we take some initial configuration of the seed tile. Okay, so here is the seed tile. Then of course on the one side vertical frame will grow like this. Vertical frame will grow, and on this side horizontal frame will grow. Once this is grown enough, basically these two tiles will contribute here 0, here 1. So which tile can come here where there is 0 on this and 1 on this side? You clearly see that only this tile will fit here, right? And it is assumed that the temperature of the system is 2 here, and the binding strength for these tiles, these compression tiles, are 1 for each of them. Okay, so what will happen? They will combine. And here is a program I have shown you last time. So what happens? You can see that this is the seed tile here. This is the seed tile here. Now I would like to ask you, out of these two, which one is vertical frame, which one is horizontal frame? I think I want answer from you. Which one is vertical frame, which one is horizontal frame? These are computational tiles. So that I just want to make sure that you understood it. Yes. So there are these two tiles. You can see that their combination is north, east, south, west, right?
First one is vertical.
This
And
one is
second one
vertical. So this is north, this is east side, this is south, and this is west. So east side is not growing, right? Correct. And No, so maybe we should draw it like this, one. So I should write it like this: north, east, west. This is our seed tile, right? Right? I'm not sure why I'm writing one. So this I can write. One will come. This is the vertical, okay. And tell me what are the numbers on this? This is the horizontal tile set. What is the number here? Vertical means you see this side it is not going right. Sorry, that is a seed. Sorry, I think I should write it down nicely. This is seed 0 0 1 1. This is how the first one is there, seed tile, right? Now vertical. So one thing will attach here. So this side it should be 0, right? Vertical. Yes. So out of this, which one will come here? Can you tell me? So this should be 1, right? So this is going to attach this side. Something should go there and something should come here. Yes. I want answer from you because I just want to make sure that you understood it now. Yes. Is it correct or wrong? Sorry, vertical this side should be 0, right? Yes. This should be 1. This should be 1. This should be 3. Is it correct?
Yes.
What about horizontal? Horizontal growth will be on this direction, right? So this side should be 0. South. West should be 1. Horizontal, this side should be 1. And this side should be 2. Do you agree?
Yes.
Good. So this is how, so these numbers you can actually understand in this sense, right? Similarly, you can write down these numbers. So basically, these are symbols you can think of, 3 and 2. In the tiles here, I have used colors 0 and 1, right? But here, so that means I have to use 2 colors or essentially 2 numbers. In the program, I have written 2 and 3. I hope you understood it, everything, right? And these are the binding strength. So this is for 2 and this is for 3. For 2 color symbol, for 2 symbol in these computational tiles, the binding strength is 1, and for 3 the binding strength is 1. Okay, and the 3 is for for other ones. So you can express it, actually this is the shorthand way of writing it 3, but you can write different ones. So I ask you to change this number to 2 and see what happens. Or can I, in your programs, can I make 2 more things? Because see, 0 growth is of course not there, right? So there is only one number left, 1. So 1 binding strength is 3. Okay, so this is growing it. So let me show you. Here, I hope some of you might have already write these commands. Xgrow binary counter ties block is equal to 2. So block is equal to 2 means I am increasing the size. Now you can see that is growing, right? This is the binary counter. And if I see the errors, you see these are the places where the errors are, these red spots. Probably you can see that these red spots, right? So please play with this xgrow, simulator to see what is happening. Okay. So the same thing, I see so many errors are happening. So till now, 28 errors have happened, mismatches errors in. So why these errors are happening in? So let me explain to you. Okay. This is another one, Pascal triangle mod 2 or Sierpinski triangle. By the way, this triangle was discovered before Pascal by some Indian mathematician. So I leave it as an exercise for you to find out who has done that. What it is known as in India. Earlier those before Pascal, but anyway, I'm calling it as Pascal right now. Pascal triangle mod 2. So now you see that here again there are 4 computational ties. We have 4 computational ties and 1 seed tie and one, this is horizontal and this is vertical, right? Horizontal and vertical ties. So now, can you tell me what is the function? So this is, remember, this is one input, this is one input, this is one output, this is one output. So output 1 is input sum operation. You can see that it is XOR operation. And output 2 is input 1 XOR input 2. Can you see that this function is here XOR in this case? In the previous case, it was what? You see, in this case, this function was output 2 was AND operation and output 1 was XOR operation, right? In our case here, Sierpinski triangle, it is XOR operation in both the cases. So there is a symmetry. Okay. Any question at this point? Any question? Okay, so let me show you. So basically, if I write down as a, I want to simulate these things. So I will again write it down like this. You see the Sierpinski triangle set. I am taken from those examples which I have shared. You can find it in the xgrow thing. So you see that this is the seed tie and horizontal, vertical, and all those things are there. And this is these are all 4 computational ties here. These are all computational ties. Okay, you can see that this is the corner seed tile. This is right, and then this is left, right, and these are the 4 computational ties. The binding strength. You see here. Note that we have written 2 1 1. So 2 is enough for 1. So this is for 1, this is for 2, this is for 3. 1 is binding strength is 2, and for other ones the binding strength is 1 and 1 1, right? Let us simulate this and see what happens. Okay. So now I go here, I'll write down the command. I have renamed them as a Pascals or tiles, and block is equal to 2 means you will see a bigger ones. You see, can you see the nice Sierpinski triangle created? Are there any errors? The question is that. You see there are 3 errors, 4 errors. You can see that. Can you see that? These red spots? 1, 2, 3, 4. Now 7 errors are there. Okay. So because of errors, you can see that the pattern is a little bit distorted, but this is how it is creating. Any question at this point? Please ask me questions, because, or if you are understanding it, fine, but otherwise you can ask me a question so that I can explain to you anything. Okay, so you can see that a lot of errors are happening here. 14 errors have happened till now. This is the Sierpinski triangle mod 2. Okay, fine. This was a simulation for Sierpinski triangle. Now, so key challenge is error control. How do we control the errors? As you can see that there are so many red spots are there in the simulations, right? Those are the places where error occurred. So how do we control the error? So what is the source of error? So source of error is unfavorable attachments. The first one is mismatch error. What happens those ACGT strings, I'll show you these ACGT strings here. These strings when they combine, sometime so if two tiles should attach, if this should be complementary matching to this, for example, you see TCTTG. So AGAAC, this is perfectly complement, right? So they should match. But what happens sometime? So this tile may partially attach to something else also. There may be a possibility. Okay. So because of ACGT, the free hand and another free hand, and they partially match at certain places. So that means there may be A, then here it is T, here it is C, then here it is G, here it is G, then here it is C. So this partial mismatch gives you attachment, and that creates an error. That's a very basic problem, partial mismatch. Okay. So an unfavorable, so mismatch error and unfavorable attachment that only partially matches the adjacent tiles can occasionally become locked into place by succeeding attachments, right? So this is something very important problem. Error. Facet error. A tile that attaches unfavorably to a facet entrance allows the attachment of incorrect tiles nearby. And nucleation error occurs when an assembly grows from a tile other than the designated seed tile. So normally assembly should grow from seed tiles, seed configuration, but it may happen that it grows from somewhere else. That is known as nucleation error. So let me give you one example. So in this kind of arrangement, temperature is 2. You see what will happen. So here it may happen that, so what tile should fit here? This red tile should fit here, UV, right? You can see that red tile should fit here. Yeah. So this red tile should fit here, right? This tile should fit here. Because this V is matching here, or no. Yeah. This U is matching here and this UV is matching here. So U and V is matching here. So this should fit here. But what happens? Actually, something else may happen. It may happen one tile from this side and one tile from this side is matching, right? And this kind of attachment is, this is something that is a possibility, right? This also creates an error. Okay. So safe attachment or invertible systems, a tile system is an invertible system if and only for all assemblies that can grow from the initial assembly, all possible attachments are safe. So for example, this is safe attachment. This is safe on the top, and this is unsafe attachment. Okay. Now, the mismatch error, I'll give you an example in the binary counter case. What happens? As you can see that here, this tile should attach, right? The second number tile should attach because this 0 and this 1 are matching. This 0 and this 1 are matching, right? So this should attach. But what happens? This will attach. Why? Because this one and this one is matching, and this one and this 0 is partially mismatched. They may partially mismatch. That may be a possibility. And so once this is happening, there is a error. Got it? There is a computational error, mismatch error. This is an example. So that's what you see the red spot, when there is a error. Okay. So what we need to do to correct the errors, we require error correcting tile sets. So that should not change the tile model. Tile systems are designed to have error correction mechanism. Two most common errors are crystallization error, nucleation error. So let me show you an example. What is the meaning of crystallization error and nucleation error? Here is a Sierpinski tile system. So you can see that this is a Sierpinski tile system, that Pascal triangle mod 2. So suppose the frame is like this, what will happen? This green tile will attach here, right? Because this 0 0 is matching, right? So this green tile will attach, another green, and this is how this will complete, right? Things, right? If this kind of configuration is given to you. Okay. Crystallization error happens if the one red tile wrongly attached here. You see that red tile, this 0 matches with 0, and this one partially mismatched with this 0. So this, what will happen? This tile will attach wrongly at this place. So this is how it is attached. Once this is attached, this is a mismatch, right? At this place, and then wrong things will grow. So this is an example of crystallization error. Got it? So how do we control the errors? In fact, Eric Winfrey gave the first idea. So normally in the error correction, what you do, if suppose we are speaking to each other, right? If I say something to you and you are unable to understand, so you will say kindly repeat. So repetition is the crude form of error correction. Similarly, normally in our communication system or our information storage systems, if we want to correct the errors, so what we do, we repeat it efficiently a certain number of times so that we can correct the errors. So same thing people started doing here, and Eric Winfrey created what is known as proofread tile system. In the proofread tile system, so error, a tile is blown into 2 by 2 or in general k by k blocks, where the information on the surroundings is blown, so kind of replicated, and because of that you are able to control the errors. So error rate is down because of this. But unfortunately, the problem with this proofread system is that system quite bigger. So proofread by error control Winfrey, right? So what we do, each tile set here, so there are some input output whatever configuration is there, right, is broken into these 4 blocks, so 2 by 2 block. This is 2 by 2 block. So OP1 is here copied, OP2 is here copied, IP1 is here copied, and IP2 is here copied, right? And these 4 tiles are internally connected. So basically, I think you might have heard one popular say in Hindi, right? Ekta mein Shakti hai, right? So the same thing. All these things are, if together in a cluster, then chances of error are less, right? It will be difficult for someone to throw one tile because of mismatch. Okay, so this is something was used by Winfrey. So in fact, in particular, for example, this Sierpinski triangle, these are the corresponding proofread tile set. For a Sierpinski triangle, so all this information is blown towards the things, and then these are internally connected. So in fact, how this will help, let me explain to you. So what happens now, each tile and the frame tile is replaced by four blocks. So you see this is a repetition. So one block is here, all these 4 tiles are internally glued, these 4 tiles are internally glued, and 4 tiles are internally glued, like that things are growing, right, in this direction and in this direction. So once this frame is created, right? I want to fill things here. So what will happen? 0, 0 was there, remember? So if there is a mismatch now, partial mismatch that happens here, so partial matching, partial hybridization here. Now, because of this, what will happen? It forces further mismatch in the neighborhood. You see, another wrong will happen, and the whole no tile can attach at this location in that case, and the whole thing will fall off, and a new system will grow. Why the whole thing will fall off? Because you see that I'll show you in the simulation again. Look at this simulation. This is the 2x2 proofread error correction by Winfrey. Here is a program for doing that. I've written the tile set. So let us see how to compute it. Here's 2x2 tile set, which is given. Now I'm going to simulate it. Now you see it is creating with no errors. You can see that there are no errors. Right? So obviously the number of tiles are more now, right? Number of tiles are more, but error rate is dropped. So you see little error here. Okay. You can see that they are perfectly shaping. Any question at this point? Again, I'm asking you any question. So you can see that errors are corrected because of blowing the tiles. Each tile is blown into 2x2 block here, right? So I'm using that tile set now to simulate, and you can see that errors are not there, right? You can see that such a clear picture is there. Till now there is no error. Okay, you see that the whole thing is there is no error at all anywhere. You can play with this, you can pause it, you can run it again, all kind of things. You can export the movie, you can cool it, so you can change the temperature. I will talk about these things later on, when I'll say that what happens when we do the change of the temperature or the value of GMC, GSC, and what are those things. I'll talk about it. You can see that here some GMC is 17 and GSC is 8.6, right? What are these things? Which I'll talk about some thermodynamic explanations to these things. Okay, so this is proofread. So this is the tile set which I simulated using this xgrow simulator. Now, what is nucleation error? So you see, nucleation error is something that if there is a first tile attaches with a weak binding strength, in that case, second tile attaching secures the first tile, and other tiles can attach the forms a layer of possibly incorrect tile set. So this is the nothing but known as nucleation error. It's creating a whole bunch of incorrect tiles at place. Now, another scheme which is very interesting. So one drawback with Winfrey proofread tile set was that it is creating, so suppose you want to create a array of certain size, say 10 by 10, it is creating 4 times more, right? So it's a bigger shape is created. We don't want that somehow. We want to control the errors in efficient manner so that we are not increasing the shape or size. Of course, tiles you need to increase. That is the thing. That is something has to be there has to be a trade-off. So John Rife, Sudhir Sahu, and Penguin. Sudhir Sahu and Penguin were the PhD student of John Rife when they invented these things. Now, Sudhir is, I think, in Google, and Penguin is at Harvard, professor at Harvard. John Rife is still at Duke University. So, in fact, one of my student, BTech student, Shalin Shah, he went to do PhD with John Rife. And he's done good work working with them. So if you want, you can also go for it. And it was a pretty good scholarship. It is $6,000 scholarship. He got. Okay. So what is this compact allocation scheme? Now you see that what we have done here. See, now you can see that discrepancy triangle. We have blown the things. So 0 is 0, 0. So now there are how many? Actually, in the input output function, I will show you later on what is input output function. There are 8 computational ties now. There are 8 computational tiles, 1 seed tile, and you see that 2 vertical tiles, so two vertical frame tiles, and 1 horizontal frame. And this kind of combination is going to reduce the error rate. How to arrive at this solution, I will show you in detail in my next class actually. Okay, but let me show you another example for binary counter. You can see that in the case of binary counter, we have done the similar thing. 8 computational tiles are there. Seed tile, uh, horizontal frame, there is a single type of tile. Vertical frame, there are 2 kind of tiles. And now these tiles, now you see that there are 4 colors: 0, 0, 0, 1, 1, 0, 1, 1. 4 colors can attach to each other. So here it is 0, 0, 1, 1. So 0, 0, 1, 1, only this tile will come. So this thing will come here, right? This thing will come here and attach here, right? Like that, the whole growth will be there. So let me show you. Here is a tile set for this. You can see that we have, seed tile, vertical frame, horizontal frame, and these are the 8 computational tiles and their corresponding binding strength. So now let me show you. How do we see that there is no error here when we do a computation here? Now this time, since this is done, this invented by Sudhir, you see that the binary counter tile set I have simulated for you. You can see that the growth is pretty smooth. There is no error in the binary counter. The previously binary counter simulation, you have seen many mismatch errors. Now with this compact error correction mechanism, there is no error actually, right? Any question at this point? Again, I am asking. You see that so binary counter is created on this right hand side. Vertical things are created. This is binary counter. I think you can, you can actually take a picture or see what are the tiles in details as well. But I'm not going to do that anyway. Okay, so this is a binary counter 4 color tile system. In fact, John Rife and his students also produced what is known as 8 color tile system. I have drawn it by hand. So here there are 16 tiles, computational tiles. In the first binary counter, there were only 4 computational tiles. In the error correction scheme, there were 8 with 2 colors, with 4 colors. And now there are with 8 colors. You can see there's 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1. All these 8 possibilities will give you 16 computational tiles. And I'll show you here is a encoding for it, and now you can see that this encoding will do simulation. Let me show you. You see 8 colors, 16 computational times. Again, there is no error. Error rate drops further, You can see that nicely created, right? Any question again at this point? I will show you how these tiles are created in much more detail. What is the function, corresponding function. Right now, I'm showing you the simulation. Okay. So in fact, this is up to 8 colors. John Rife actually and his students, Sudhir Sao and Penguin, they posed an open problem in 2004. Can we simplify the RS5 construction and extend the construction to a more general construction where we can have more colors? After 8 colors, they could not solve it. In fact, later on, myself and one of my collaborators, Naveen Kashyap, we solved it. And also, Eric Winfrey himself and, uh, David, they have also proposed a solution, KV overlay construction. I'm not going to describe it, but I think if you are interested, you can look at it. We proposed, in general, 2 raised power k color construction. So here is a 32 colors, which are actually solving the problem. Sorry, six. Yeah, this is 16 possibilities, right? 16 color combination. Okay, so let me show you this 16 color. Here is a program for that. 16 color, 32 computational tiles. You can see that it's a bit lengthy, obviously. Now you see the growth is now a bit slow because more and more tiles are there, but there are no errors. Right? This is for 16 color. Anyway, in fact, we have done many more things. We have done given tile set for gray counter, Fibonacci pattern, and in fact, we have done also tile set for modular arithmetic expression. We have developed a front end for DNA computing known as xTile. This is all done by BTech students who are doing this course, by the way. So I think some of you can also take up the challenge and do certain things. We have also SST tile set implementation for DNA pen. I will show you those things. I have also sent a team of students to Harvard University for presenting the work on CAT. So they have created, they have participated in biomod competition where we wanted to create Taj Mahal at the nanoscale using DNA. Of course, we have done it for a single strand, but of course, it will require much more complex design. We have not done it yet, so it's still an open problem. So if anyone is interested, they can actually do that. I think I will now show you some references. So this is the reference of PhD thesis by Eric Winfrey, which I have shown. put it in the Google Classroom. Penguin chapter 3 describes these error correction mechanisms, compact error free mechanisms, which you can read chapter 3. So Paul Rotman, I already told you that is also interesting thing. Or if you want, you can look at the paper directly. So paper, this 4 paper, this proofread tile set, for Eric Winfrey, which is for blowing the things. This is the compact error correction paper. Okay? And these are the hardware things. This is a very nice book on tiles, tiling and patterns by Grunbaum. But I think this is if it is available, that's really nice. You can also see in terms of study problems like program size, complexity of self-resembling certain patterns. So one can ask different kind of questions. How much time, complexity? Just like that in algorithms, if you want to solve a problem, what is the complexity of solving that problem? Big O of what? Those kind of questions can be asked. So I will slowly go into more details about these things. One thing I have shown you counter, which is unbounded right now. So it is growing indefinitely. So what if I want to design a counter which I can say count say up to 10 or count up to 12? So how do you design a tile set for that? So I give it as an easy exercise for you to think. You have the tile set for the binary counter, unbounded binary counter. Can you design a tile set for counter which can stop at a given time depending upon where you want to stop? So I will probably talk about it in a bit more details later on. So if you have any questions, again, I'm asking you, if you have any questions, please do ask me. These are some more references. I'll talk about Xstyle also later on. Any questions? Okay. So did you, by the way, did you started doing these simulations at home? Yes, Tulsi, did you tried it? You tried it something, right? I think I've seen.
Yes, sir. Xgrow, I tried.
Okay. Yeah, so I think you should try some more things. I will share some of these tile set with you, whichever I have shown you today, and you can do some simulations. And I think that's all for today. So we'll do a couple of more things in the next class. In fact, I will try to give you more explanation about these error correction mechanisms, and after that I'm going to look at how to solve certain arithmetic problems. So addition of two numbers, multiplication of certain numbers, doing some evaluating some arithmetic expressions, how you can solve these things using these tile problems. So this is a nice thing. With the tiles you can solve many kind of problems, and you can ask very nice questions like complexity questions. How much time, what is the time complexity of solving a problem? Okay, so those things we are going to discuss in the next class. Thank you.
Sir, what is the exam pattern?
Exam questions will be objective. So I think it will be objective. So whatever we have covered till now, we can ask some objective questions with you. So if you do it carefully, read it. By the way, if you have any doubt anywhere, anything, please do ask me on WhatsApp group. Because that is available 24/7. You can reach me, and I can help you. In whatever way possible. If something, I think I have given you some reading material. Unfortunately, there is no very good textbook on these topics. Somebody has to write it, but there are some notes taken by some of my students. I will try to share it with you. Which will give you some idea. But before that, I think I need to cover a couple of more topics before we can enter into those things. So I think I'll probably ask you 10 questions or 12 questions, objective type questions. You can answer it. Okay.
Okay, sir. Thank you.
Any more question? Please do try these things at home, with xgrow simulator. Okay, so I think that's all. I'll stop sharing my screen now and end the stream.